Hello and welcome to another online digital math lesson for pre-algebra. And we are going to actually finish up chapter 11 today. We're going to talk about section 5 about graphing nonlinear functions. I'm going to be honest with you, I'm going to be real with you guys right now, that this lesson is going to definitely require you to pay a little bit of attention. Maybe a bit of attention, because we're going to be talking about graphing. And we talked about graphing before. We talked about how to graph linear functions. If you guys remember, linear means line. But today we're going to be talking about two different nonlinear forms. And typically, students don't really like graphing, and they definitely prefer linear to nonlinear. So before we can go forward with these two nonlinear forms, what we want to do is we want to kind of recap how to graph linear functions. And to do that, we're going to get our good friend Desmos back out here. Ayo, Desmos, where you at, dog? Here I am. All right. Here, I use Desmos.com in order to graph a linear function. All right. If you guys remember, your linear function falls under the form of y is equal to mx plus b, where if I have this equation, y is equal to 2x minus 3, then the slope m is equal to 2, and the y-intercept b is equal to negative 3. And if you remember how to graph this, you would start with your starting point, which is your y-intercept. And because this is at negative 3, it's going to go down 1, 2, 3 in the negative. All right, so this is our y-intercept. And then from there, you would have a slope or a rise over run, where 2 is the amount that it goes up or down, and we always want to go over to the right, positive 1, if we have space. The rise over run, we would rise 1, 2, then run right 1. So you go rise 2, right 1. 1, 2, right 1, 1, 2, right 1, 1, 2, right 1. And you see all these dots, they form a straight linear line, all right? And you notice that this is a positive slope, so it's going uphill. This is stuff we haven't done in a very long time, all right? But this is an example of a linear function. And before I graph anything, I can tell that this is linear. Well, how can I tell that this is linear? Well, I would look at the function. If the function is y is equal to 2x minus 3, I would say that this function has what I'm going to call a regular x. The regular x is just a regular x, right? It can have a number next to it, but this isn't anything fancy, right? There's a difference between a regular x and what I'm going to call a fancy x. And the regular x is just something like this. Or another example of a linear function, y is equal to 1/2 x plus 5. I'm just making this up. But I know that this has a regular x, so it's going to be a line. All right, y is equal to 2x plus 12. Is that a line? Yes, because it has a regular x. Let's go ahead and give you an example of what I'm going to call... I'm going to go ahead and call this a fancy x. Y is equal to x squared minus 3. Because it has a squared, we're going to call this guy fancy. Oh, he fancy. All right. Y is equal to the square root of x minus 3. This is a fancy x because it has a square root. That's not going to be a line. Y is equal to the absolute value of x plus 2 minus 3. This is a fancy x because it has a square root. But whenever we have a regular x, it's always going to be a linear function, and we're just going to call it a regular x. All right. So when I first start teaching people how to graph functions, I always want you guys to have a good idea of what it's supposed to look like in your head, because the way that the x is, it actually tells you what family it's from. In fact, when we graph, we can say that the function y equals x is a parent function, so it is the parent of all linear functions, and this, because it's a regular x, is going to be a line. Now, if I change the x and make it fancy by putting a square or a square root or absolute value root or a cubed root. All right, that makes it fancy. Or maybe I put an x in the denominator. That's also another fancy x. It's going to change the way the graph looks. So what we need to do is we need to go back on Desmos and see what happens if I change the x and make it fancy. Alright, so here we have our function just kind of by itself again. And what would happen if I do change the x and I make it fancy? Like what would happen if I put x squared there? And is it still a line? No. This is a shape called a parabola. Alright, so parabola. Alright, I kind of just typed it in here. It's not going to do anything because that's not a function, right? But this is a shape called a parabola, which makes it a U-shaped graph. And any time that I have x squared, it's always going to make a parabola every single time, all right? So it's a fancy x, but this specific fancy x is called a quadratic function, and it makes a parabola. Like if I change this and get rid of the 2, all right, still a parabola. If I get rid of the -3, it's still a parabola, right? What happens if I put like a negative sign in front of it? Well, it flips it around, but it's still a parabola. All right, so what we're learning in this lesson is how to graph nonlinear shapes. And this is an example of a nonlinear shape. This is a parabola, and it's not a line. It makes a U-shaped graph. This cannot, by any definition, be considered a line, because a line, by definition, is straight, right? Like a line would look like this, right? But once we make the x fancy, it changes the shape. Now, there's 2 different ways that we're going to talk about how to graph these functions. We're going to talk about how to graph these using tables and patterns. So we're going to go ahead and practice first learning how to graph using a table. Now this is an example of a table where I'm going to have 3 different columns. A column for our x values, a column for our function rule, and then a column that has our ordered pair that we're going to graph. Now this guy is what we're going to call our function rule. And I'm going to try to graph y is equal to x squared. Now I'm going to go ahead and put my x squared here. Some people like to put the whole function in. That's fine. And what we're going to do is we are going to choose our own values for x. We're going to choose values for x. And the truth is you can pick any numbers that you guys want. But for me personally, I'm going to pick the values -1, 0, 1, and 2. I'm going to try to pick small numbers, all right? And again, I want to have a few different numbers. In your book, it says pick values from -2 to 2. I'm okay if you guys have this value, and I'll show you guys why soon. All right, and all I'm going to do is say if x equals -1, and my function rule is x squared, what I'm going to do is I'm just going to go ahead and plug in values -1 for x. If x is equal to -1, then -1 squared is equal to what? Well, since my x is equal to -1, my y, in this case, y is equal to -1 times -1 is going to be 1. Okay? If I graph this point on my graph, -1 and 1, I look at my graph over here, -1 and 1 is right here. Then I do the same thing. I'm just going to go ahead and plug in 0 for instead of x, and I'm going to get 0 times 0 is 0. So I have a point right here. And I'm just going to go ahead and do the same thing 2 more times. 1 squared is 1, so 1 goes there. So 1 and 1. And 2 squared is 4, so I graph this point. All right, 1, 2, 1, 2, 3, 4. And all of a sudden I have this shape. And it looks like it's making a parabolic shape. Now what would happen if I put -2? Well, -2 would actually be the same thing, because I learned whenever I graph parabolas is that parabolas are always symmetrical. meaning they look the same on both sides. It's like there's a mirror in between them. And if there's a mirror in between them, that means that there's going to be another point on this side the same width. All right, so this is our graph. Missed it. All right, this is our graph, or it makes a parabolic shape. That looks kind of weird. I'm going to go ahead and try to erase this, but it's going to erase part of the graph too, probably. Yeah, it is. All right, and this is my graph. This is a parabolic shape, and this is the graph for y is equal to x squared. All right, let's try another one. Let's just try another one. All right, so now we're going to go ahead and try to graph this function, y is equal to 2x squared. And because I see that it is x squared, it's a fancy x, I know that this is supposed to be a parabola. All right, now what's good news for us is if we know the shape what it's supposed to be and we get something completely different, then we know something went wrong, we should probably go ahead and check Desmos. But if we want to go ahead and graph using a table, all we're going to do is put our function rule, all right, in the middle, and we're going to get 2x squared, and we're going to pick values of x. My suggestion is to usually pick really small numbers, and usually at least one negative number. It's usually a good idea to have that, at least right now. So our function rule is 2 times something squared, 2 times something squared, 2 times something squared, 2 times something squared. And because we already picked our values of x, we know the first coordinates are going to be -1, 0, 1, and 2. Now, we're just going to go ahead and plug in our values. When -1 gets plugged in here, our exponent happens first. -1 times -1 is positive 1. 1, so this is 1, times 2 is going to be 2. Our first point should be at -1, positive 2. All right, that's our first point. Our next one, we're going to plug in 0, and 0 times 0 is 0, and 0 times 2 is going to be 0. So we put a point here at 0. Now, if we plug in 1 right here, this becomes 1 times 1 is 1, times 2 is 2, so we have a point at 1 and 2. So it looks like it's making a parabola for us. And then we plug in this one, and this is going to be 2 times 2 is 4, and 4 times 2 is 8. So when I go 2 in the x value, I'm going to go up 8 in the y. And because this is symmetrical, it's going to be the same thing on both sides, and it looks like we make a parabolic shape. And it makes that U-shaped graph. Kind of what we expected. Now notice I multiplied by 2 and it got taller faster. So whenever you multiply by numbers bigger than 1, it gets expected to be a little bit taller. And if I multiply by numbers smaller than 1, it probably gets a little bit smaller. So we're going to go ahead and graph one more function for you guys. And notice we have a different exponent. This is going to be a cubic function. This is something that we call a cubic function. We're going to find out what shape cubic functions make. But I'm going to do the same thing. I'm just going to go ahead and use a table. I'm going to go ahead and put x cubed in there. And I'm going to go ahead and plug in -1 times x cubed, 0 cubed, 1 cubed, and 2 cubed. And we're going to see what happens. So when I multiply these out, -1 times -1 times -1 is -1. 0 times 0 times 0 is 0. 1 times 1 times 1 is positive 1. And 2 times 2 times 2 is 8. Now if you struggle with cubes, you can use a calculator. And in the calculator, sometimes they have a button that says, that has like a caret button. And this just means an exponent where you can type in your number. And then you can go ahead to the power of 3 and that will work for you. But when I graph this, I end up getting a shape that looks like this. This is going to make a snake-shaped graph, So we're going to call any cubic functions snake-shaped graphs because it's going to look like this where it goes through these points and makes a snake going here. If you have any problems with this, you guys can go to desmos.com and that's going to help you with your graph shapes. But every time we're going to have this, it might be helpful to actually use -2 as an x point because that's going to give you this point down there. All right. Good luck with your